let's start again the second section this morning. And I welcome Professor Olga Manko from Lebedev Physical Institute at Moscow. So please, Professor, you can start.
Good day, dear colleagues. First, I want to thank Professor Viktor Vasilievich Dodonov and Alexander Viktorovich Dodonov for their kind invitation, which gives me a possibility to participate in this conference. Also, I want to congratulate Professor Dodonov with his 75 jubileum. Dear Viktor Vasilievich, happy birthday to you. Also, I would like to tell that the period of my life when I was a PhD student of Professor Viktor Dodonov was very good and fruitful period of my life. Thank you very much, Viktor Vasilievich, for opening my way in the science. Значит, my talk is about quantum states of inverted oscillator in the probability representation. From the very beginning of quantum mechanics, the language on which speak classical statistical theory and quantum mechanics was quite different. So it was a dream to close the language of quantum mechanics to the language of classical probability theory. The states in classical probability theory in statistical mechanics is usually described by probability distribution function. The state of quantum system in standard formulation of quantum mechanics usually are determined either by vectors in the Hilbert space or by the density operators acting in Hilbert space. The vectors in Hilbert space are associated with wave function psi in the case of pure state, or with density operators associated with pure or mixed states. The density matrices are described by its matrix elements, so matrix elements of the density operators in some representations. In order to make the language of quantum mechanics more close to the classical one, it was attempts to introduce different representations. So it was constructed Wigner function, Blachintsev mixed density matrix, Kusimi-Kano function, Glauber-Sudarshan function, the table of probability for spin states made by Wouter. So different representations of quantum states were constructed, but all of them, of course, have some properties of probabilistic distributions, but they're quasi-distributions. So they don't have all properties of probabilistic distributions. The connection of Wigner function and measurable probability distribution function, optical tomography, was introduced in the papers of Bertrand and Fogel-Riskin. The experimental realization of optical tomography scheme was done in the group of Reimer. One of the attempts to describe quantum picture of the world in the language more close to classical-like is the method which is based on the associative product of functions. So it is condensation based on associative product of functions, star product. For example, it was done in paper of Bayen. The probability representation of quantum states in the case of continuous variables was introduced in the papers of Stefano Mancini, Vladimir Manько, and Paolo Tambesi. In the case of non-discrete variables. And in the case of discrete variables, so-named spin tomography scheme was introduced in the papers of Viktor Vasilievich Dodonov, Vladimir Ivanovich Manько, and me. The consideration of symplectic tomography scheme in the frame of star product quantization was done in the papers of Neapol and Lebedev groups. Neapol University and Lebedev Institute groups. And recently, very interesting paper was published in Entropy. It was a series of papers of our group, and additional the paper of Guzon. They were published in a journal named Entropy, which belonged to MDPI publishing house. First, I will speak a little about general scheme of star product quantization. This consideration is based on the material which is published in the papers of our and Napoli group. All known quasi-distribution functions can be obtained using the different pairs of operators. Operator D, we named quantizer, and operator U, we named dequantizers. These operators give the possibility to map the operator acting in Hilbert space A to its symbol function of the operator. And the map is of the form. The symbol of operator FA is equal to trace of the product of given operator A and the quantizer operator U. There exists inverse transform by which we can reconstruct the operator from its symbol. So the operator A is equal to integral of symbol of operator multiplied by quantizing operator. If we know exactly this pair of quantizer and the quantizer, we know the scheme of quantization based on star product. The map, which we discussed, provides the possibility to introduce the star product of function FA and FB. So if we have two operators A and B, and they have symbols FA and FAB, the symbol of operator A multiplied by operator B is of the form. It is trace equal to trace of product operators A and B and the quantizer operator U. The star product of the function FA and B is the star product, not usual. And it can be presented in integral form. So the star product of two symbols of operator, FA and FB, are equal to integral from product of symbol operators with the integral kernel. This integral kernel K can be expressed in terms of quantizer and dequantizer operators. Since the product of operators is associative, the star product of symbols of the operators is also associative. It gives additional equations which must satisfy the kernel. One can use the formula of quantizer and the quantizer operators to write the evolution equation for symbol of density operators. For example, let us consider the von Neumann equation for density operator. And we introduce the symbol of density operator as trace of the product of density operator with the quantizer operator. And we introduce the symbol of Hamiltonian as the trace of product of operator of Hamiltonian with the quantizer operator U. Then we see that our von Neumann equation can be expressed through through the symbols of operators, and we receive the equation for the symbol of operator of density matrix, F rho. The equation, if we know the Hamiltonian, the equation for given Hamiltonian H has the general form of integral equation, which you can see here. So it's the integral equation in which we see the symbols of density operators and the symbol of Hamiltonian. Now let us return in a classical picture. A classical particle with position Q and momentum P is described by a point on the fast space. If the particle is in the medium with non-zero temperature T, it is described by distribution function f from Qp due to appearing of fluctuation of position Q and momentum P. So the probability distribution function f at Qp is non-negative. And the function dw determines the probability to find the classical particle near the point Qp in fast space in interval dq/dp. So dw/Qp is f at Qp, our distribution function, multiplied by dq at dp. And our probability distribution function is normalized. Integral from fqp dq/dp is equal to unity. The state of quantum particle is determined by the wave function. The sense of modulus of wave function is the density of probability to find particle near position Q in an interval dq. The additional fluctuation, if our quantum particle is in media with temperature T, determines the appeared, and then we have to determine the state of the particle by density matrix. For example, for mixed state of oscillator, density matrix is of the form. Here, the coefficients pk is non-negative, and the sum of coefficients pk is equal to unity. The pure state of oscillator also can be determined by density matrix. The probability representation of oscillator states was introduced in the articles which is written below. It turns out that the wave function determines the probability density W from x mu nu. It is conditional probability distribution of homodyne quadrature or of position x. And x is equal mu multiplied by q plus mu multiplied by p. This position x is measured in reference frame p' in fast space. The function w at x mu nu, which is conditional probability distribution, was named symplectic tomogram. So if we have in fast space reference frame, and then we rotate this frame and squeezed this axis of the frame, we receive new frame Q', P'. And the rotation parameter is theta, and the scaling parameter is S. Our parameters mu and nu, which determine the reference frame in fast space, are expressed through scaling and rotation parameter. And in this scaled and rotated reference frame, the coordinate x is measured. So we receive x equal to q cosine theta p sine theta. First we rotate, and then we scale and receive the coordinate x measured in the ensemble of scaled and rotated reference frames. The conditional probability omega from x mu nu in the case of classical oscillator is determined by Radon transform. So we can express our conditional probability omega from x mu nu through the probability distribution function f at qp using the Radon transform. Our function omega from x mu nu is non-negative, and it is normalized. The symplectic tomogram of classical system was introduced in the paper of Vladimir Manько and me. In the case of quantum picture, the tomogram of quantum oscillator state can be expressed through the wave function as coefficient multiplied by square of modulus of integral of such a form. The density matrix can be reconstructed from density operator using the inverse Radon transform of the tomogram. So here is the reconstructed formula for density operator. We see that if we know conditional probability distribution function omega from x mu nu, with this integral transform, we can reconstruct the density matrix. For example, the ground state of quantum oscillator has the wave function C0, and it can be determined by symplectic tomogram omega 0, which is of the form of Gaussian. For example, for nth excited Fock states with wave function Cn, here Hn is Hermite polynomials, we can write and determine the state by symplectic tomogram. Ground state symplectic tomogram and n excited Fock states tomogram is normalized. For symplectic tomogram, the inverse quantum Radon transform has the form. So we can reconstruct density operator from symplectic tomogram with the help of such expression. Here we see exponential function from operators Q and P. It means that in the case of symplectic tomogram, the quantizer operator D is of the form coefficients multiplied by exponential functions. And the variables in our general form x1, x2, x1, x2, x3 are equal to x mu nu. The dequantizer in the symplectic tomography scheme operator U has the form of delta function from operators Q and P. The kernel describing the star product of the symbol of operators is the trace of the product of two quantizer and one dead quantizer. So in the case of symplectic tomography, it is of the form coefficients multiplied by trace of the product of two exponents in one delta function. And in explicit form, in terms of parameters which determine reference frames, it is shown on the formula X on the end of the page. Now let us consider the inverted classical oscillator. The Hamiltonian of classical inverted oscillator, in which we put m mass frequency omega equal to unity, is of the form It is p quadrat, 1/2 of p quadrat minus squared minus 1/2 of q quadrat squared. One can check that there exist two expressions, q0 and p0, which is initial moment of time is equal to usual position and momentum, and has the form q multiplied by hyperbolic cosinus of t minus p multiplied by hyperbolic sinus of t, and p0 is equal minus q multiplied by sinus hyperbolic t plus p multiplied by cosine hyperbolic t. These expressions satisfy the differential equations, which are equations which has to satisfy integral of motion. So we have the expression, the equation for inverted oscillator. Let us consider some properties of inverted quantum oscillator in probability representation. It's necessary to add that some properties of inverted oscillators recently was discussed in the papers of Professor Schleich and Professor Wouters with co-authors. One can check that the quantum inverted oscillator with a Hamiltonian, which is written here, has the integrals of motion. So the Hermitian operators Q0, P0 of such a form satisfy the equations for quantum integrals of motion of the following form. Also, in initial moment of time, operators Q0 and P0 are equal to usual operators of coordinate and momentum. The green function of the Schrödinger equation in position representation satisfies the system of following equations. These equations can be obtained using the method of integrals of motion Q0, P0. And in the initial moment of time, the green function is equal to delta function from y minus x. The green function is analogous to the green function of usual harmonic oscillator with frequency omega squared equal to unity. But the condition omega squared equal to minus unity is used to get the expression for the propagator of inverted oscillator from the propagator of usual harmonic oscillator. So we obtain the following equation. We obtain the green function in moment 2. Значит, using this green function and the initial condition for wave function of the inverted oscillator, when calculate evolution of the wave function. This wave function at the moment t more than 0 determines the tomographic probability distribution describing the inverted oscillator. This integral relation of the wave function with the tomograph system with linear in position q and momentum p integrals of motion provides the possibility to obtain the evolution of the tomographic probability distribution of inverted oscillator. The operators integrals of motion a from t and a deg of t can be expressed through our operators Q0 and P0. They satisfy the commutation relation. And in the initial moment of time, they're equal to usual annihilation and creation bosonic operators. We construct the Hogerian states of the inverted oscillator using the definition. The action of operator A on the state give us alpha multiplied by this state. For initial moment of time, the cogherent state has the following form. Let us solve the following problem. To compose the behavior of the symplectic tomograms of the inverted oscillator states, which initially at moment t equal to 0 were prepared as state of usual oscillator with frequency omega equal to unity and mass and equal to unity and Planck constant we put equal to unity. It means that the initial ground state of usual oscillator with the Hamiltonian of usual oscillator where we have plus before Q squared is the wave function written here in position representation C0. And then this function and the state of oscillator begin to evolve in the potential of inverted oscillator. So the potential minus Q squared, half of it. The tomogram of the state with the initial ground state wave function omega 0 has the form given by relations. So it is expressed through the wave function. And in explicit form, it has the form of Gaussian. We demonstrate the possibility to obtain the evolution of tomogram using the relation. We can reconstruct the tomogram using our scheme based on associated, on quantization, dequantization based on star product of symbols of operators. So our tomogram of ground states in the moment t is equal to trace of density operator and delta function. The density operator in the moment t can be expressed through the density operator initial moment of time by the formula exponential function from minus I Hamiltonian t, density operator in the 0 moment of time, and multiplied by exponential function from I Hamiltonian t. And here we take as a Hamiltonian on inverted oscillator. Then we have the expression that our tomogram of ground-like state of operator of oscillator in moment t is equal to trace from product of density operator and initial moment in time and delta function from such argument. Here we see using the property of operator trace that we receive our exponentials with Hamiltonian inside the delta function. We can use the property of position and momentum operators then. These operators in Heisenberg representation, QH and PH, which for the inverted oscillator have the form repeating formally the classical formula, and it gives us the possibility to solve the kinetic equations by replacement in known symplectic tomographic probability representation formula, the parameters mu and nu by parameters mu h and nu h, expressing the relation of Heisenberg operators with the usual operators Q and P. It is easy to do for systems with quadratic Hamiltonian in position and momentum. So we consider such relation. Nu parameters mu h and nu h expressed through the previous parameter mu and nu, which determines the reference frame in fast space. For this, we write the equality in such a form, and we see that it means that our parameter mu h is equal to previous mu multiplied by cosine hyperbolic of time plus nu multiplied, here is a mistake, by by sine hyperbolic of t. And nu h is mu multiplied by sine hyperbolic from t plus nu multiplied by cosine hyperbolic from t. Then we can write the symplectic tomogram for the evolving state of the inverted oscillator using the change of parameter mu by parameter mu h and parameter nu by parameter nu h in the initial tomogram. And then we receive the tomogram of inverted oscillator ground state in moment t. This is normal probability distribution with zero mean values and varying dispersions. Basic meaning of this tomogram is that for mu equal to unity and nu equal to 0, it provides probability distribution of the position of the inverted oscillator in moment t. And for meaning mu equal to 1 and nu equal to unity, it is equal to probability distribution of the momentum of the inverted oscillator at time t. For both cases, the initial state was prepared in ground state of usual oscillators. The dispersion of the position and momentum are equal and satisfy the Heisenberg uncertainty relation at any time t. Here is written the Schrödinger-Robertson uncertainty relation with coefficient, correlation coefficient R. Значит, the correlation coefficients R is more than 0, no less than unity. And it is equal to following expression. So we see how the correlation coefficient is depending on time for the state of inverted oscillator. For t equal to 0, the correlation is equal to 0. And for large time, it's approached unity. This means that there are present large fluctuations with large kinetic energy contributions to the behavior of inverted oscillator. We consider such system if the initial state of oscillator is coherent one. Then, using the same procedure of changing mu to mu h and nu to nu h, we get the time evolution of the inverted oscillator tomogram of the form. For the initial state, which is Fock and Fock excited states, we also, making the same procedure, can obtain the tomogram of excited Fock states of inverted oscillator in the following form, where h is Hermite polynomials. Also, we can introduce some characteristics addition of the quantum states of the inverted oscillator. The state which is determined by symplectic tomogram. So we can introduce for the state the Shannon entropy. For the initial state to be coherent one, the initial entropy is read as square root from p multiplied by exponential by exponenta by sum of parameters mu squared and nu squared. For inverted oscillator, the entropy at time t have the expression written on the end of the page. We have shown that the quantum mechanical system can be described by standard probability distribution functions. We considered the example of inverted quantum oscillator and calculated such distributions and studied their properties.
5 minutes left.
This new method open new possibility to solve new and old problems of quantum mechanics and quantum information theory. This description gives us possibility to make closer the language of quantum mechanics on this example to the language of statistical physics, and to use the probability distribution functions for the describing of the states of quantum objects. That's all. Thank you.